recording here. All right. So last day we went through chapter 7, and right now I am completely blanking on what that was. Oh yeah, just the experimental design and things like that, what to do. It was basically a recap, including the interactions. And so the last section that we didn't quite get to is 7.6. So using a two-way ANOVA model. So with interactions. Okay. So I just want to lay out the hypotheses that we're testing when we run that ANOVA, and then we'll get into chapter 8. And I have only I planned on only doing 8.1 and 8.2. I think we were supposed to get into 8.3, but we slipped behind a little bit last day, so I'm just pacing ourselves a little bit now. So, and I mean, what we get through, we get through. Don't get through, we won't get through. So, so what we have, right, is the theoretical model is mu plus, and then we can use alphas or taus, it doesn't matter. Alpha I plus beta j, right? So we've got our treatments, and our block, or treatments maybe, blocks. And then what we have is plus gamma ij. This is the interaction. And you guys are probably better at drawing gammas than I am. They're a little bit tricky, right? So here, this is a gamma, actually a lowercase gamma. And kind of a fun background story. Gamma is called gamma because it looks like a camel's head. So it's supposed to look like a camel's head. And C and G are interchangeable in Greek. So for the Greeks, C is gamma. So it goes alpha, beta, gamma. Right? And because gamma is C, because it's a camel and it looks like a camel's head. So that's just kind of a fun detour. But anyways, usually my gammas, oh, say that again?
I said it's a good one.
Oh. Or usually my gammas look like this. Kind of weird looking, but you'll want to, yeah, practice your gammas. So just be flexible if my gammas aren't very pretty. And where we assume that the errors follow a normal distribution centered on 0 with some fixed standard deviation and independent. Right, this is basically just a summary of our conditions. Right, the errors are centered on 0. With even spread, and they're independent. Right. So so that's just basically a summary of the conditions. It's nothing new, right? But we don't usually I haven't really been writing them out that way, but we definitely can. And so here's our theoretical model. And so we've got some treatment, we've got a blocking factor typically, or just factor 1, factor 2, and then we've got this interaction term, gamma, that we've introduced in chapter 7, but that's the only new thing. So for each of these, right, we've already seen the output for our ANOVA, right? We get an F for factor 1, we get an F for factor 2, and we also get an F test for the interaction term, right? And so now we're testing 3 different hypotheses. So when we run an ANOVA with an interaction term, we are running 3 hypothesis tests simultaneously. Clean that up. Simultaneously, right? The first one, the null hypothesis, is that, and whether you use alphas or taus, it doesn't matter. I'll use alpha because then we got that nice flow of alpha, beta, gamma, right? And so alpha 1 is alpha 2, which is all the way up to equal to alpha I, if we've got I levels of factor A, and they're all equal to 0. Right? And so just put in brackets here that this is for factor A. And then of course the alternative hypothesis, this is where we started. So this hypothesis we've been testing all along, but we want to know if some level of this is not equal to 0. Right. So that's the first test that we're checking. The next test, same idea, right? But just for the betas instead, right? Beta 1 just equals beta 2, going on and on and on, equal to beta j. Oh, that should be a capital J. Just for the parameters is equal to 0. This is for factor B. And same idea, the alternative hypothesis is that some beta j does not equal 0. And then the last hypothesis that we're checking, and I'm going to bump these up so I've got them all on the same page. Whee! There, that looks okay. The last one is that all of the gamma ij's equals 0. So this is for our interaction. And the alternative hypothesis is that some gamma ij is not equal to 0. You might wonder why we would use all gamma ij are equal to 0 when here we listed each one explicitly. I guess we could have used the same, so all beta j's are equal to 0. But it's just nice to see them listed explicitly here when we can. But remember all the interactions, right? If we're making room for I by j factors, right, we've got I by j combinations. And so all those would give us interaction terms. And it might just be a little too much, right, to list individually. So that's why we just list, okay, all gamma ij's are equal to 0, or there's some interaction in there that's not 0. Okay. So we already saw the output for when we have a significant interaction term. right? And so, and we've already looked, and last day we looked at, you know, what kind of graphs can we look at to figure out if we think there's an interaction term, should we include it, should we not include it? I would say what we arrived at was, if you're not sure, just include the interaction term, and then if it's not significant, then who cares, right? Then you could either pull it out or just leave it in there and show that that it's not significant. So the difference with how we approach the analysis of all these things is going to depend on if we have an interaction term or not. And so if interaction is present, what we have to do is we have to use the conditional averages instead of the marginal averages for things like hypothesis testing, confidence intervals, effect sizes. And so if the interaction, so if interaction is present, we use conditional averages for, and can I just write HT for hypothesis testing, confidence intervals, and effect sizes. Right. Otherwise, we can use marginal averages. We can use marginal averages. So what that looks like, right, is if you've got, so factor, let's put B up here and factor A over here, right? Regardless of how many kind of combinations you've got here, let's say you have that many combinations, right? It could be huge depending on how many levels of each factor you have, right? These are your conditional averages. Whereas these guys, oh, maybe I should use a different color. Whereas these averages are the marginal averages. Right, and so if you've concluded that there's no interaction between factor A and factor B, then we can just look at these marginal averages to summarize what factor A behaves or has for behavior, and then marginal averages for how factor B behaves. But if we're saying that there is an interaction between these two groups, right, or these two treatments, or, well, I guess we can call them factors, then we should be looking at, okay, well, conditional on, you know, factor B being in group 1 and factor A being in group 2, right, maybe over here, then what's our effect size? What are the, can we do a hypothesis test, right? And so then we would look at the conditional averages. Okay. So.
Oh, sorry. I mean, just,
Oh, yeah.
well, I'm kind of refreshing my head here.
Oh,
So,
it's okay. Yeah.
so we established hypothesis, right? So all three hypotheses. So then we do ANOVA table.
That's right.
Where in the ANOVA table you can see F value and P values, right?
That's right.
Then if you see that P value is less than alpha, or let's say the default 0.05, then
That's right.
it's significant, right?
Yeah.
Then we build confidence intervals
Mm-hmm.
and effect sizes for both factors and interaction.
Well, so it depends on if we have an interaction, then you're going to build your hypothesis testing and confidence intervals and effect sizes should be focused on the conditional averages, right? Which are the averages in these overlapping cells. Because then you want to know, okay, well, how does factor A influence factor B, right? If there's an interaction. If there's no interaction, then you can just use the marginal averages like we've been doing. So,
probably later on if you have an example.
I don't think I started this note, but then I decided, no, this was for later. We won't have time, we won't go through it, but I am going to point you to the chapter summary in chapter 7 because it does go through a full analysis. So just kind of how I did with the chapter 5 when I gave you guys the general analysis, they do that for you in the chapter summary for chapter 7. So maybe I'll write that down.
Okay.
But the last thing that I've got here in my notes, just so I don't forget to write it down. So if there is no interaction, interaction effect, we focus our analysis on the main effects. We focus our analysis on the main effects, right? Which are factor A and factor B. Right? Which I think you would do anyways. If you're saying, okay, there's no interaction term, I don't really care about that. It's just if there is an interaction effect, then these marginal averages aren't actually going to tell you very much, right? What's one of the examples that we've kind of looked at? They've got a ton of examples in the textbook to kind of guide different situations, but of course I can't recreate all of those here. But let's go.
What are we basically looking at? The marginal averages?
So for the marginal averages, that's what you would use to do your confidence intervals, your hypothesis testing. So here, if we just look at those figures from last day, right? This is for the pigs data. So pigs were given B12 in combination with antibiotics, and then we measured their weight gain. So there's only 2 levels for B12 and 2 levels for antibiotics. We find that all 3 are significant, right? Especially this interaction term. So what we're saying is that, okay, where's the pigs data here? Oh, there. So what we would do, right, is we would figure out our analysis, because we decided that there's an interaction term, right, then our confidence intervals would be centered on the no category, the no yes category, and the yes no category. So what I'm going to do is I'm just going to steal this copy into our notes for today. Paste, and I'm also going to steal I'm going to try to steal just that one. So what we would have, right, is in your table, you would have antibiotics on one end. Antibiotics, actually, let's put B12 just to match how we've been doing it. B12 and antibiotics here. Antibiotics. And for our levels of B12, we've got 0 and 5 milligrams. And then for the antibiotics, I think we've just got no and yes. No, 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 yes. What are these? Oh, I'm just halting because this no and no are referring to no B12. Yes and yes are referring to yes, there is B12, right? And so here we could call this no, and yes, they get B12, right? And it happens to be 5 milligrams. Okay? And so here, because we've got this interaction going on in here, right, we could find the marginal averages, right? But we should be focusing on the conditional averages, right? So we should use conditional averages oops, triangle. Use that opportunity to change it to for hypothesis testing, confidence intervals, and effect sizes, right? Because if I tell you that there's an interaction between how much, if they get B12 and whether they're on antibiotics or not, and I want to know what the weight gain is for these pigs, then you wouldn't go on to tell me just about how they would do it for, or how they would increase in weight with just B12 and just antibiotics, right? I would be interested in those conditional averages, right? Because here, this is the marginal average, right? So here, this would be just B12, and this would be just antibiotics. So I guess I did have an example.
I understand.
Cool?
Yeah, I understand.
Nice. Yeah, so the only difference is which averages we should be using. But then how we do the hypothesis test, we haven't done a ton of hypothesis testing. We really should be focusing on confidence intervals. So confidence intervals and effect sizes, we can do hypothesis testing, but we can usually get away with just confidence intervals. And so here, did I put it? No. Okay. See the chapter 7 summary for a complete analysis. Right. So just for examples of how to do those effect sizes and confidence intervals and all that fun stuff, they go through and do that. And I'm pretty sure they might actually use the pigs data. Let me just check here. Well, they've got a couple of different ones. They really go through and analyze a bunch of different data sets. It is the pigs data for the chapter summary. So then you can have a look and see. I think it's because the pigs had the most obvious interaction that they use that one. Okay, cool. All right. Shall we get into chapter 8, or any questions about chapter 7 before we do? No? All right. So it's going to look crowded, but there's a page break here, so just going to go for it. So chapter 8, remember in chapters 1 through 4, right? Chapter 4 was just kind of like a bunch of extra things that we could think about, that we could consider, right, in regression. Chapter 8 is going to be very similar, but for the ANOVA case, right, where we just talk about and expand on ideas that we already have, introduce a couple of new things that we could do, but they're just calling it additional topics in ANOVA. So the first topic that we're going to talk about is Levine's test for homogeneity of variances. Homogeneity of variances. So far, right, we've just been, we know that one of our assumptions, right, so we know one of our conditions for ANOVA is roughly equal variances. Roughly equal variances, right? Which so far we've just been, you know, check the box plots. So check the side-by-side plots, whether that's box plots or dot plots, it doesn't matter. I think what you'll find is for smaller data sets, right, if you've only got, you know, 3 observations in a group, the box plots don't really make sense because they have to have at least a 5-number summary. And so that's going to be hard to do. So then maybe dot plots are better, right? So dot plots or box plots, it doesn't matter, but I would say use dot plots for small sample sizes. We can also check the residuals. Check the residual plots or plot for even scatter. Right. So what's another option that we've had? We've calculated the max standard deviation over the min standard deviation, and to make sure that it's less than 2. That last one is probably our most robust measurement so far, right? For if we can assume roughly equal variances, or if we need a transformation here. But Levine's test is actually going to give us a hypothesis test for equal variances. So Levine's test gives us a hypothesis test for equal variances. So the null hypothesis that it's testing is if sigma 1 squared is equal to sigma 2 squared is equal to sigma 3 squared, which is equal to all the way up to sigma I squared. What we're saying here is that there's no difference in the variances. So there's no difference in the variances. And then the alternative hypothesis is that not all variances are equal. Not all variances are equal. Or if you want to show, say, some ij or sigma ij squared is not equal to another ij squared, I don't know, sigma ij squared, it doesn't matter. It's just easier in words if you say not all variances are equal. Okay. One thing to note here, right, is this is one of those situations where we actually do not want to reject the null hypothesis, right? And so notice, to be able to assume equal variances, we do not want to reject H naught, right? So that's a little bit different from what we usually want, right? Usually we're aiming to reject the null hypothesis. So, but as long as we remember what the null hypotheses are, we should be able to figure out what we want and what we don't want. So here, if I want to be able to assume that I have equal variances, right, that means that I'm not rejecting H naught. And there's no way that you're ever going to calculate Levine's test by hand. But notice that it's got kind of a similar layout to an ANOVA, right? And so that's the reason that they held off on introducing Levine's test until now, is because it's another ANOVA that we do. But I mean, R is just going to do it for you. Any software, any self-respecting software will run a Levine's test for you. Okay. So, but just as a little bit of background, I guess. Levine's test uses the absolute deviations between the observations and their group medians, so not the means, because that would be the residuals, right? So they're very similar to the residuals, but not really. So Levine's test uses the absolute deviations between the observations and their group medians, and then it applies an ANOVA to those absolute deviations, right? So then it compares the means of those absolute deviations. So then applies an ANOVA to those absolute deviations. So that's kind of easy to think about if we've got a one-way ANOVA, right? Because then we've just got a treatment and we can look at, you know, the differences in the groups. Gets a little bit bigger to think about if you've got a two-way, but it works the same way, right? Then we just look at each of the cells, right? And so what I'll do here is I'll just say for two-way data, this applies to all combinations of cells. My dog just came back from outside and she wants me to greet her. So this applies to all combinations of cells. Oops. Okay. We always make software do these calculations, right? So it's again, it's not one of those things that you need to know how to do. We always make software do these calculations. Oops. Okay. Cool. So that's Levine's test. You can play around and see if you can find it in our, I think it might be part of the output, but I can't remember. But yeah, so you can play around with that and see. But this kind of background theory is not something that you need to know or anything, but it's just good to know where things came from. So, any questions? No.
None so far.
Oh, none so far. You'll hop in if you have any, I hope. But it just feels weird to not ask for questions. That's why. All right, so let's get into section 8.2. Although, okay, all right. 8.2 is where we talk about multiple tests. Oops, multiple. Okay, so multiple tests, right? The only thing that we've seen, but I saw a couple of Tukey's HSDs on your lab 4s, so that's great. But so we've seen Fissures Lsd, right? The Fissures least significant difference before. Now I'm going to introduce 2 more, right? And then we'll compare the 3 of them, and it just kind of depends on which error rate you want to control. So there's a couple of different error rates. Well, there's the type 1, type 2 errors, depending on what's more of a concern for your data and your situation. But let's just do a little refresher, right? So when we run multiple tests, when we run multiple tests, whether that's hypothesis testing or confidence intervals, it actually doesn't matter, right? Either way, we expose ourselves to more type 1 errors, right? So, or I'll just say in general, we expose ourselves to more decision errors, right? And then what I'll do in brackets is I'll say type 1 or type 2. We're going to be differentiating between, there's a family-wise error rate. Right, so this is if you run multiple tests. So this is in a family of multiple tests. And then there's the individual error rate, and that's the error rate that we're usually, concerned with. If I run one hypothesis test, what's my error rate, right? And so the individual error rate is the error rate of one hypothesis test or confidence interval. right? So usually kind of earlier, right, we were concerned with the individual error rate, right? If I run one hypothesis test, what's the probability of a type 1 error, type 2 error? And then now we're more concerned with, so what we were concerned with Fissures Lsd was the family-wise error rate. Okay, if I'm doing, you know, 5 hypothesis tests, then what's my family, so that's my family of multiple tests, then what's the family-wise error rate? Each time that I run a hypothesis test, for example, I expose myself to a type 1 and a type 2 error. All right, so what I'll do here is I'll got arrows all over the place. Each time I run a hypothesis test, for example, I expose myself to type 1 / 2 errors. So earlier, right, we introduced Fissures Lsd as a way of decreasing the family-wise error rate, as a way of decreasing the family-wise error rate, right, for multiple tests. So we calculated the difference, the least significant difference, and then we compared all our differences that we were interested in with that length, and if it was longer than that length, then we said that it was significant. So the ones that we're going to introduce today, and there's a lot more, right, but here are kind of the main players in the real world. And so the 3 ways, oh, actually, I don't want to say that because it makes it sound like there's only 3 ways. The 3 most common ways to deal with multiple tests are the first one, we'll say Fissures Lsd, Fissures least significant difference. The second one is called a Bonferroni adjustment. Bonferroni adjustment. And I think I've even hinted at the Bonferroni adjustment and said, oh, just divide your alpha level by however many comparisons you want to do. And basically that's it. So, but we'll talk about it. And then there's Tukey's HSD, which stands for honestly significant differences, or honest significant differences. So if we had to rank these, right, then the Fissures Lsd is quite liberal in the sense that, okay, we just want to, you know, are there any differences here? I'm not too concerned with concluding that something is a difference when it's not, right? And so here it's quite liberal, whereas the Bonferroni adjustment is quite conservative, right? So it's likely that you're going to miss actual differences, but maybe that's better. And then Tukey's HSD is kind of moderate, making it a good option just in general, right? So we're going to focus on confidence intervals because it's going to be the easiest thing to talk about, but also because they're laid out the same way for each of these. And a lot of these are just going to use confidence intervals, right? Because if the difference of 0 is in there, then it's not significant, right? And so we can use confidence intervals in that way. So all three methods produce confidence intervals. Okay. And they all look like yi bar minus yj bar plus minus some margin of error, right? So this here, this is the difference of interest, right? So it's going to look at all the different combinations of I and j and build some confidence interval around those differences. So where the margin of error is some critical value. Now here's where I disagree with the textbook. I actually don't like to have 2 letters. So what I'm going to do is I'm just going to call it a C subscript V, right, for a critical value, which for some reason I have a hard time saying, but anyways, doesn't matter. Times the square root of the mean squared error times 1 over ni plus 1 over nj. Okay. So here, this CV is a critical value that differs for each method. Oops, it should say method. Everything else stays the same, right? The mean squared errors from your ANOVA where you determine that there is a difference, so that's why you're even on this path. And then the sample size in group I, the sample size in group A, they'll all be different, right? And so the only difference between all these methods will be the critical values. So we'll talk about what each of these critical values are for each of the methods. But again, of course, software, if you tell it to run a 2P's HSD, it'll just do it for you, right? And same thing, if you get it to use the Bonferroni method, then it'll just do it for you. Okay. So the first one, let's talk about Fissures Lsd. So Fissures Lsd, the critical value is just a T star, right? With the mean squared error degrees of freedom, right, which is just n minus I, and the individual alpha of choice, right? So usually that's 0.05. And the individual alpha of choice, usually 0.05. Okay. One thing to keep in mind about the Fissures Lsd is that it's mostly controlling the individual error rate, right? And so here, Fissures Lsd mostly controls the individual error rate. Right? We said, okay, if I'm doing all these comparisons, then I want to be able to control the individual error rate, right? And so I don't want to make have an alpha level, so have a 0.05 probability of making a type 1 error every single comparison that I make, right? And so the Fissures Lsd is one way that we can avoid that, right? Introducing that 0.05 level every single comparison that we do. Okay. So the second method is the Bonferroni adjustment. Bonferroni adjustment. This one has, so the Bonferroni adjustment has an emphasis on controlling the family-wise error rate. So that's the opposite, essentially, of the Fissures Lsd. So it has an emphasis on controlling the family-wise error rate. Oops. The family-wise error rate. And like I said, the Bonferroni adjustment, let's see if I did put a colon. In general, if we want to make M comparisons, so if we want to make M comparisons, we replace alpha with alpha over M. And so instead of, so just as an example, for 5 comparisons, we would use alpha over 5, which is 0.05 over 5. So now for each comparison, you would decrease your alpha to 0.01, right? But then your overall family error rate is still 0.05, right? So you're trying to bring that down. The critical value, let's see if I used a different color. I did not. The critical value is still going to be a T star, right? But it's going to be a T star for a 100 times 1 minus alpha over M confidence level, still with mean squared error degrees of freedom. So that's the same. It's just your, which is n minus I. It's just that you've accounted for the alpha over M in your T star, right? So now your confidence level is going to be quite a bit higher, right? Okay, so both of these, so far, Fissures Lsd and the Bonferroni adjustment, if we're making confidence interval, they both use T star. The only one that doesn't is the Tukey's HSD. And so the third one, Tukey's HSD, which stands for honest significant difference. Honest significant difference. Okay. Tukey's HSD is kind of like a balance between the two. So if we look back here, right, Fissures Lsd mostly controls the individual error rate, whereas the Bonferroni adjustment control is really trying to control the family-wise error rate. So now Tukey's HSD is a balance between those two. And so Tukey's HSD is a balance between controlling individual and family-wise error rates. Okay. And so we can also say, so this is a way to control the family-wise error rate. Control the family-wise error rate while retaining the usefulness of the individual intervals. So while retaining the usefulness of the individual intervals, Because what happened over here in the Bonferroni method, right, or the Bonferroni adjustment, now we're making huge confidence interval, or our confidence level gets huge, right? So instead of a 95% confidence interval, now I would make a 99% confidence interval, for example, right? Which would mean that my bounds are huge. And so I've got this wider confidence interval. And so that's what it means when we say, while retaining the usefulness of the individual intervals, right? We want our intervals to be precise enough or kind of tight enough to tell us something. Right? And so here, like I said, the only difference is that the critical value is something, so a Q over the square root of 2, okay? Where Q is from the studentized range distribution. This is not something, it's not a table that we're gonna have, it's not something that we're gonna use, it's just, I'm just telling you where it's from, and then software will just use it, right? It would be a table, but no, we don't care about that. So where Q is from the studentized range distribution. Okay. And the studentized range distribution, how we pick our Q, well, it's going to be based on the number of intervals or comparisons, the alpha, and of course, again, the mean squared error degrees of freedom. Okay. So that's where that Q is going to come from. Okay. So like I said, the only way that these things change is in the critical value, and Fissures Lsd and the Bonferroni adjustment both use T-stars, just different versions of it. And then Tukey's HSD is the only one that uses something else. Right? And like I said, we use software for all these calculations, of course, always. Okay. So as a comparison of the three, right, just to kind of wrap it up here, as a comparison of the three, if we're looking at the Bonferroni and Tukey's HSD, my B looked so weird. Bonferroni and Tukey's HSD, we make sure that the overall type 1 error rate is low. So they're more concerned with rejecting H0 when we shouldn't have. That's bad, right? So it depends on the situation that you're working on. But we have to make sure, so what these guys focus on is to make sure that the overall type 1 error rate is low. So here, I'll just add that we would use these ones if we have specific differences in mind ahead of time, right? So it totally depends on your situation, but we would use these, or one of these. We would use one of these if we have specific differences, in mind ahead of time. Differences in mind ahead of time. Okay. So here, right, not to leave anyone out here, Fissures Lsd, what does Fissures Lsd do? Fissures Lsd is really more, if you're concerned about missing actual differences, right? So if a type 2 error is a problem, right? So if missing actual differences is a bigger problem, use Fissures Lsd, right? I'll put in brackets here, if we need to avoid type 2 errors. So it depends on the situation, right? But I will add Fissures Lsd is most useful if you're doing some sort of exploratory analysis, right? Where you just want to know, okay, are there any differences here? You're opening up for potential differences being significant that aren't necessarily, right? And so here, use an exploratory analysis to see what differences might exist, right? It's opening up for telling you that there are differences that aren't necessarily differences, but in exploratory analysis, maybe that's just, you would just want to get a feel for things, right? And so these are your 2 or your 3 kind of methods that you can use, and it depends on what you want to emphasize. We would only use, so in an analysis, we would only use one of these methods. But I would say there's no harm in checking all of them, right, to see if there's any discrepancies. But there is no harm in running all of them But there's no harm in running all of them to see if there are any discrepancies. They're all supposed to do the same thing, right? So if you're finding discrepancies, then that's interesting too. And maybe you want to look at why that might be, right? And then you need to decide if, okay, if I say these two things are different and they're not actually, is that bad? Or is it worse if I actually miss some actual differences? Because then you want to use Fissures Lsd. All right. Any questions? Because that's all I've got for today, and I think that's pretty good. Let's see here. Who's all here? Hey guys. Cool.
None so far on my side.
No, that's all I've got, Manuel. Does anyone have any questions for today, I guess?
Nope.
Nope. All right. Then I guess you'll hear from me on Monday, right? What day is it today? No questions so far, Luis says. Great. Well, that's all I've got. So we'll keep going through chapter 8 next day. We'll keep going. So we did 8.1 and 8.2 today. Oh, and I'm going to change the assignment 9 due date to be a little bit later because we shifted things around, right? So I'll bump that due date, but should be okay. All right. So then that's it for us today.
Thank you.
Thank you. See you guys later. Well, I won't see you, but anyways, have a good weekend. Bye, guys.